Good evening, everybody, and you're very welcome to our webinar this evening for maths teachers. It's all about problem solving for Leaving Certificate Ordinary Level students. Thank you very much for joining us this evening. I'll introduce you shortly to Mike and to Jim, who are the main event here. But to just introduce myself, my name is Conor Walker. I'm the head of post-primary publishing. And what I wanted to do initially, actually, before I handed you over to the guys, I want to just take this opportunity to mention that this webinar is in conjunction with the publication of our new Active Maths 3 book, which is now in its third edition. So what we've done with Active Maths 3 in this new edition is we've been very much tailoring it to the requirements of the current ordinary level maths classroom for Leaving Certificate, and we've placed a particular focus on making the book revised to be more concise. Also, we've reviewed it to make sure that the more recent exam paper questions and style of questions, such as the problem solving questions, are included in the book. And we've also included very strong grading and signposting for differentiation, if that's something that you need to cater for in an ordinary level classroom. So if you'd like to learn more about the books, you can check them out by visiting folens.ie. There you can see samples of the textbook and various other digital resources and solutions that we offer with that. The book itself will be available very shortly after Easter. So if you'd like to get in touch with your Folens rep about that, please feel free to do so. They're available for calls or appointments at a time that will suit you. They can arrange sample copies for you, and they also can provide information around support for book rentals. So if you'd like to find out who your local rep is, please go to the folens.ie website, input your school name or roll number. That will throw back the details of a rep, and you can get in touch with them. So really what I want to do now is just hand you over to our team. So just by way of introduction, I think first Mike Keating will be speaking, and Mike is a member of the Active Maths Author team. He taught at Closh in Eskelga in County Kerry, and for many, many years has been involved in marking state examinations. And Jim McElroy is a special advisor on the Active Maths series and teaches at Castleknock College in Dublin 15. I'll hand you over to Mike just now, but to let you know, if you'd like to post questions to either Jim or Mike, please feel free to do so. You can do that by clicking the Q&A button and posting your question there, or there's also a chat function. If you click the little speech bubble button across the top of your screen, that will allow you to post your questions there, and we'll get through to as many as we can by the end of the webinar. So with that, I'm delighted to hand you over to Mike Keating. So Mike, if you'd like to take control, I wish you the best of luck.
Thank you, Conor. So I'll just share my screen here and hope that everybody can see it. And slideshow and from beginning. So I hope you can all see that.
We can see that, Mike. Thanks.
Excellent. Very, very good. Okay, so as Conor has already said, now our presentation this evening is problem solving for Leaving Cert Ordinary Level. And our presentation, I suppose, is divided up into two sections. The first section, we'll just deal with some of the current research in the area, in other words, current research and problem solving in mathematics for second level students. And then we will move on to a series of problems. So I will take 4 problems and walk through those problems using some of the ideas from the research, and Jim will follow on then with 5 other problems. So we'll just get started straight away. And the first question we're asking here is, what is problem solving in mathematics? So I suppose with problem solving, students are faced with a problem where it is not immediately obvious what method should be employed to solve the problem. And our first quote there kind of makes that clear. Problem solving tasks usually involve non-standard problems in which the solver does not instantly know the solution or the correct solving strategy. So it's different to solving problems, which is about applying a known method to solve a problem that has already been solved. So for example, if you ask a student to divide 2 complex numbers, Z1 divided by Z2, there's a strategy for doing that, and they just follow that strategy. whereas with problem solving, it's not obvious or clear from the start how the problem will be approached or what methods will be employed to solve the problem. Now, our second bullet point there, we say one approach in problem solving involves helping students develop the type of thinking needed for solving problems rather than simply instructing students on how to solve problems. So in other words, if you give a student or your class a problem and you supply a kind of a recipe for solving the problem, then that's not really problem solving. It's not getting the student to think. So I suppose the key way or the key approach to helping students solve problems from that perspective would be to, first of all, ensure that the student knows that the answer is not obvious and that they're going to have to work and employ different strategies to solve the problem. It's important as well, I suppose, to point out to them that they need to persevere with the problem, because obviously if you can't see the answer straight off, then perseverance is a huge asset, and if you don't persevere, obviously, then you're not going to arrive at a solution. I suppose something else that helps, or that I found helps anyway in problem solving, is if you do a bit of group work or pair work with the students and getting working in groups and discussing problems. So that is the difference, let's say, between problem solving and just solving problems. Okay, so how do we help students to become problem solvers? So if we look at our first quote here, teachers can greatly influence students' progression in mathematical problem solving. Asking the right questions or leading students to think about a particular problem on a higher level can help students' problem solving experience become more productive. And I suppose asking the right questions is a key phrase there. So in other words, we don't want to give the game away straight away by asking questions that are going to guide them towards the solution. So we just release a certain amount of information, and depending on the ability of the class, then you will decide whether or what amount of information you're going to release to the student, or what questions you're going to ask the students. But you can't ask questions, in other words, that is going to lead them straight off to the answer. Now, our second quote, one central goal of teachers should be to develop students' persistence in solving problems. The atmosphere where teachers force students in investigating and finding new solutions or solving strategies can influence students' ability to solve problems. So I suppose this is a real challenge, particularly at ordinary level, because obviously you get a lot of pushback from students at this level when they cannot solve the problem immediately. So I suppose it's good advice really to have some simple problems to start off with, and also to have graded problems that will suit the ability of the class. So in other words, more difficult problems for the better students, and for the students who struggle a little bit, then have a set of easier problems. Okay, but in order to build their confidence, I think we need to do that. And of course, another important thing to teach students when problem solving is that there are many different approaches to solving problems, many different approaches that we can take, the so-called multi-representational approach. So even if a student solves a problem in one particular way, they should be asked as well then to solve it in another, or use another approach to solve the problem. Now, our next section is on questions, and of course teacher questions are vital in problem solving and in guiding students towards a solution, and asking the right questions is also important. So the literature tells us that there are 4 types of question. You've got the factual questions. So these are just questions where the answer is predetermined. So for example, what's the highest common factor of 8 and 12? So we use those from time to time. Guiding questions. So guiding or process-based questions are related to problem-solving processes. Guiding questions help students to progress. So later on, we'll be looking at a problem where the student is asked to find the area of a pentagon. And of course, you would leave them off to find the area of the pentagon, but if they're starting to struggle, then you could ask a guiding question. So for example, can you divide the shape, the pentagon, into a set of right angle triangles and rectangles, and hence you should then be able to move on, if you know the correct formulas, to solve the problem. So that's an example of a guiding question. Task supervision questions then verify that the task is being solved. So for example, how will you measure that is an example of a task supervision question. And then finally, probably the most important ones, the probing or open solution questions. Probing, speculative or open solution questions lead students to think on a higher level. So for example, what could that mean? Or what do you think might happen then? So there's more than one right answer to these questions. So as I said, questions are obviously important and important so that the student can progress. Now, problem-solving lessons. So this is what the academics are telling us about problem-solving lessons. Usually in a classroom, problem-solving lessons have 3 different phases. First, the teacher introduces the task by showing the problem and motivating students to work on it. And also the teacher makes sure that everyone has understood the instructions. So that is perhaps the most important part of the problem-solving lesson, so ensuring that the student understands the question. So you could, for example, ask them to underline keywords, ask them to underline words that they don't understand, ask them to ask questions about the problem, and so on. So starting off the problem-solving lesson is the key part of it, because we don't want to lose them at that stage. So then students try to solve the task while the teacher helps and supports them. And then finally, at the end of the lesson, the looking back phase reviews students' achievements in solving the task. So in the looking back phase, you could be looking at different approaches that could be taken to solve the problem. So once a student has used one approach, it's always a good idea to ask them to do it in another fashion or another way. Okay, now these are some problem-solving strategies, and you've all probably seen these before. I think they date back to the early days of Project Maths, where we got posters with the different type of problem-solving strategies. Now I think there are 10 in total, and if I'm not mistaken, we're using about 8 of them tonight in the set of problems that we are doing. Okay. So systematic listing, making out a table, draw a picture, which is always a good idea. Simplify the problem, solve a simpler problem, in other words, and that should help you to move on to a more difficult one. Find a pattern, trial and improvement, generalization of the problem, solve the problem by working backwards, use algebra, use a formula. So they're all the different, well, they're not all the strategies, but they are the strategies that we're pretty familiar with. Okay, so I think we're ready to move on to the first problem, and this is a nice problem. I think it looks horrendous enough at the beginning. We've a set of 5 equations and 5 unknowns, and we're asking them to solve the equations. But in this instance, the solutions come from the set 0, 1, 2, 3, 4, and 5. Okay. Now, I just listed some questions here. Obviously, you're not going to ask all of these questions because, as I said earlier on, you're just giving it to them in a plate if you do that. But here are some of the questions that will help them understand the problem. So first of all, just to ensure that they know that the values come from the set A. So the values for A, B, C, D are restricted to what set of numbers. And then another kind of follow on from that, could B be equal to -2? And why not? Well, B has to be a positive integer or 0, so it can't be -2. Another one then is, again, this is for the people who are struggling and finding it difficult. You could ask the question, if you know the value of B, how would you find D? And they scan down through the equations there, and they see that D is equal to B squared, so you would square B to get D. Now, an important property of numbers here, if I add 0 to 5, what is the result? So knowing that that is 5 will be helpful. And if I add 0 to any number x, what is the result? And also, if I multiply 4 by 1, what is the result? So again, that's going to be useful to find one of the numbers. 4 by 1 is 4, or x by 1 is x. And they'll see that popping up in one of the equations. So we look at, I think it's 3 different approaches here. So the first one is trial and improvement. And the first equation is a plus a plus a equals a squared. So they'll trial the numbers and we'll find that 0 and 3 will satisfy that first equation. So there are 2 possibilities for a at that stage. we come down then to the second equation, b plus c equals b. Again, they can trial numbers here, but quickly they realize that c has to be 0. C has to be 0. And if c is 0, then of course a has to be 3. We can eliminate a equal to 0. The third one then, d multiplied by e equals d. And again, with substitution of numbers, they'll quickly realize here that e should be 1. And that leaves us then with b being either 2, 4, or 5. When we come down to the next equation, a minus e equals b. Well, they've already found a is 3, and they've found e is 1. So 3 minus 1 is 2, gives them the value 2 for b. The next one, b squared equals d. So they've all found b now, so d is going to be 2 squared or 4. And then finally, d plus e is, we've already found d and e, so f is 4 plus 1, which is 5. So that's a kind of a trial and improvement approach to the problem. Here's another approach where we look at, now it's probably one that students wouldn't come up with, but it's no harm to run them through an approach like this, where they use the properties of numbers. So if we look at those 5 properties, we have x plus y equals x. Well, then obviously y is 0, or what we call the additive property of 0, or the additive identity. Second property, x multiplied by y equals x, so therefore y must equal 1, which is the multiplicative identity, so the multiplicative property of 1. If x is equal to y squared, then x is a square number. So we've 2 square numbers, I think, in the list. We have 1 and 4. So if x is equal to y squared, then x has a square number. Number 4, if x and y are positive, and x plus y equals z. So because x and y are positive, then z must be greater than x, and also z must be greater than y, if x and y are both positive. And finally then, if x multiplied by y equals y squared, and y is not 0, then x must equal y. You can see that just by substituting y into the left-hand side of the equation. So how are we going to use those properties? So if we scan down through it, well, we see b plus c equals b. So we're going to be using property 1 to find b. We see that d multiplied by e equals d. So we're going to use property 2 to find e. X equals y squared, then x is a square number. So d is the square number. Now it can't be 1 because we already used 1. So d is going to equal 4. And then if x and y are positive and x plus y equals z, then z must be greater than x and z must be greater than y. We've already found d to be 4, so for the last equation, then d plus e equals f. If d is 4, then f must be 5, the only remaining number in the set that's greater than 4. And we just listed out there the solutions and the property number beside it. So this is kind of an unusual approach, which is using the properties of numbers. Third approach then is, I suppose, the approach that we as teachers would be inclined to use most of the time, where we solve the thing algebraically. So the first equation, a plus a plus a is equal to a squared, 3a is equal to a squared, a squared minus 3a equals 0, factorize it, a by a minus 3 equals 0, so a equals 0 or a equals 3. B plus c equals, second equation, b plus c equals b, c is equal to b minus b, c is equal to 0, so a then has to be 3 if c is 0. D multiplied by e equals d, so e is equal to d divided by d, so e equals 1. And then for the final lot, b, d, and f, we just substitute into the other equations. We've already found values for a and for e, sorry, for a, yes, and for e and for c. Okay, so even the algebra is a nice approach to doing it in this instance, because there are quite a number of algebraic skills that they need to solve it using this approach. So there are 3 approaches for that particular problem. Now, here's the one I mentioned earlier, finding the area of a pentagon. So they're given a pentagon on a grid and asked to find the area of the pentagon. And again, as I said earlier on, if they're struggling with this, I suppose we could ask them to divide the pentagon, the interior of the pentagon, into right angle triangles and rectangle, or 3 rectangles, I think it is. So again, off they go and they divide. So the question you can ask here is, can you divide the total area of the pentagon into a set of non-overlapping right-angle triangles and rectangles? So again, they'll tease their way through that for a few minutes. And then I suppose it's no harm either to ask, what formulas do you know for finding the area of a triangle and the area of a rectangle? So even though they've split it up into triangles and rectangles, they still need to find the area of the triangles and the area of the rectangles. So here's how they should divide it. So there you can see a series of, I think it's 6, isn't it? 6 triangles and 3 rectangles. And we have the base and height of all those right angle triangles. So we can find the area of all of those triangles, and we can also find the area of the rectangles. So I just done it out there. We have 4 rectangles, or sorry, 4 triangles that have a base of 3 and a height of 1. So that'll give you a total area of 6 for those. We have 2 triangles then that have a base of 2 and a height of 3, give us an area of 6. And the rectangles, then we have one has the area 6, another has the area 4, and the smaller one has an area of 3, giving us a total of 13. And then summing all those together gives us the area of the pentagon, which is 25 units squared. Now approach 2. And again, you might ask them to do this rather than ask them to circumscribe the pentagon to begin with. So you ask them to circumscribe. So in other words, draw a rectangle around the pentagon that includes or contains all the vertices of the pentagon, and then ask them to take it from there. So the questions you could ask here, once they've constructed the rectangle around the pentagon, is ask them to divide the area between the pentagon and the rectangle into a series of triangles again and a rectangle. So again, it's actually easier to do this time once they realize that they've got to get the area between the pentagon and the rectangle. So they get this series of triangles and the one rectangle. So their next job then will be to find, first of all, the area of the rectangle, which is 7 by 6, 42, and then get the area of all the triangles plus the rectangle. Okay, and I think all that, when they work out all those areas, it will come to 17. So then taking away 17 from the 42 gives us the 25 units squared. 17 being the area outside, and if we take that away from the rectangle, you're left with the pentagon. And that's another kind of nice approach to solving the problem. Now, this one may not seem the prettiest, but at the same time, it's practice for their coordinate geometry. Okay, so where we would place the pentagon on a coordinated plane and use the area of the triangle formula from coordinate geometry. So I suppose this is one where you would actually have prepared for them, because I don't think certainly the students that would struggle would get around to placing it properly on a coordinated plane. So maybe have that one ready and ask them then to fill in the coordinates, and then they're left with finding the area of 3 triangles. And one of the triangles, of course, we ensure that one of the triangles is a vertex at 0, 0 to make the calculations that bit easier. And there you have it, finding the areas of the 3 triangles. The first one is fine, it's just directly substituting into the formula, and then we use some translations to find the area of the other 2. But when they do that and add all the areas together of the 3 triangles, out comes 25 units squared again. So there are 3 different approaches to solving the problem, and they all have their benefits. Okay. Now, here is our next problem. Jim's furniture shop has a choice of 3-legged stools and 4-legged stools. There are 5 more 3-legged stools than 4-legged stools. And when you count the legs of the stools, there are exactly 57 legs. How many 3-legged and 4-legged stools are in the shop? Okay, so again, a few questions to get started on, just to ensure that they understand the problem and that they've read it, I suppose. So is it possible to have 12 3-legged stools and 17 4-legged stools, and give a reason for your answer? And of course, the answer is no, because there are 5 more 3-legged stools than 4-legged stools, so that's not a possible combination. The second question then is how many legs in total on 10 four-legged stools and 15 three-legged stools. This is just a question just to ensure that they know how to calculate the number of legs on the stools, the total number of legs on the stools. Okay, so our first approach is trial and improvement. Okay, and this is a pretty straightforward one. We make out a table, look at the four-legged stools first of all. Now you could have no four-legged stool and 5 three-legged stools, because remember we need to have 5 more three-legged stools than four-legged stools. And then we find out there's no legs in those four-legged stools, obviously, and there are 15 legs in 5 three-legged stools. So that is a total of 15 legs. And then we continue on. We go to 1 four-legged stool, and then you have to, if you 1 four-legged stool, you're going to have 6 three-legged stools, and we calculate the total number of legs on that. That comes to 22, and we work our way down through it. And finally, when we arrive at 6, out pops the 57 that we were that we wanted. So we need 6 four-legged stools and 11 three-legged stools then to have a total of 57 legs. So trial and improvement, our first approach. Second approach is look for a pattern. Okay. So here, what I've done is, and it might be no harm maybe to give them this table as well at this level. So we look at the total number of legs as a pattern. And so if you've no four-legged stool and first one 5 three-legged stools, and that's a total of 15 legs. And then we 1 four-legged and 6 three-legged and so on, that's 22 and so on. And we build up. So we have 4 numbers there, 15, 22, 29, and 36. And you ask them then what pattern or what type of pattern are the numbers in the table generating. So quickly they will see that it is a linear pattern with a difference or a first difference or a common difference, whichever you call it, of 7. So there's a difference of 7 between each of the terms. And then another question we could ask them, because we want to find the actual term that contains 57. Do you know a formula for finding any term in such a pattern? So hopefully they'll come up with Tn is equal to A plus n minus 1 times D. And if not, we tell them. Okay, so here's our solution then. So this is an arithmetic or a linear pattern with A equals 15 and D equals 7. And we want to find n now when term n is 57. So we just simply substitute into the formula and we solve for n, and we end up with n equals 7. So term 7 is where 57 is going to appear. So there's still a little bit of work to be done here. So in term 7, how many four-legged stools are we going to have? And of course, the number of four-legged stools is going to be 1 less than the term number, and that's 6. So we're going to have 6 four-legged stools, and of course, if you're going to have 5 more three-legged stools than four-legged stools, you're going to have 11 three-legged stools. I've changed from stools to tables or to chairs. Okay, so that's approach 2. And now let's look at the algebraic approach again, the one that we as teachers would probably gravitate towards. So we let x equal the number of three-legged chairs and y equal the number of four-legged chairs. So x is equal to y plus 5. And then looking at the legs, the total number of legs. So on the three-legged stools, are going to have 3 legs, so 3x, and then plus 4y equals 57. And we solve the simultaneous equations, giving us y equals 6 and x equals 11. So that's 11 three-legged chairs and 6 four-legged chairs. And that's our third approach. Oh, sorry. Okay, so we're on to Jim now, if that's okay, to take us through the remaining problems. I'll just stop sharing.
Thanks, Mike, and good evening, everybody. I hope that you can see the presentation there from my computer. So I'm going to take us through now another 4 problems. The last one actually will have a slight pause just before it for a minute or two, where we can all consider different approaches that might be taken. But for the first 3, I'll just go through, as Mike has been doing, some different problem-solving approaches that students might take in a problem-solving lesson or could be guided to take by their teacher. So the first problem that we see here is A sequences and series problem involving a repeating pattern of numbers, and there are a number of parts to the problem. The first part is fairly self-explanatory. I suppose students would be looking to make out a table, and using that table then they would be able to answer the first part. But the second and third parts B and C, have a number of different approaches that might be taken. So in part B and part C, students are asked to calculate the values of certain term positions within the sequence and to calculate certain partial sums. So one approach that could be taken by students would be the approach of systematic listing. So looking at part C, the highest position that's required to answer part B and C will be position number 48. So a student might simply, from the beginning of the pattern, work all the way through to the 48th position. And in that way, then they'd be easily able to pick up terms 12 and 20 and 22, 44, 46, 47 and 48, and in that way answer parts B and C. And a teacher then at that stage might say to a student, well, do you think this is an efficient method or the most efficient method of solving this type of problem? Or what about if parts B or C asked for a position that was much further into the sequence, like position number 200, for example? And that might help students or motivate students then to a quicker method. So a second approach that might be taken, which does also involve systematic listing to an extent, but it involves it in the form of making out a table where the repeating pattern is more discernible. So you can see here in the table that a student might make out that if they, at the top of the table, have a row showing the 6 digits that occur in the first 6 positions of the pattern, they are then underneath each of those digits able to write down the position or the term number that is assigned that digit value. And that would then perhaps help students recognize that there is a pattern at play here that might even lead them then to an even more efficient approach, as we'll see in a minute. So, for example, a teacher might ask a student here, well, what do the numbers 1 or 7 or 13, 19, 25, 31, 37, 43 have in common in terms of the number 6? And if we just go back a slide, we'll see that all of those numbers, when you divide them by 6, they have remainder 1. And as a result, the terms that are in those positions would have the same value as term 1. And likewise, a teacher could then say, well, what about the numbers 2, 8, 14, 20, 26, and so on? What do they have in common in terms of the number 6? And again, just going back to the table, all of those numbers would have a remainder of 2 when you divide by 6. So they would have the same value as term 2, which would be 4. So in this way, a teacher could help guide students towards an even more efficient approach, which we look at here, a third approach, which we'll call finding a pattern. And here, the pattern, of course, is that repeating nature of the pattern, repeating every 6 terms. So at this stage, you would hope that students would be able to engage with that repeating nature of the pattern and recognize that because the pattern repeats every 6 terms, if you divide the term position by 6 and just concentrate on the remainder will tell you if it's the first position, second position, third position, fourth position, fifth position, or 6th position in the original 6 digits that you should be looking at in terms of the value of a particular term. And at this stage, then, a teacher could say, well, can you think of a real world context where this type of approach might be useful? So where this use of remainder division or modular arithmetic might be useful, so that if a different, maybe a completely different problem appeared in future, students would recognize that this method might be a viable method. So, for example, any context where there's a cyclical nature, where there's a repeating pattern, might lend itself to this type of modular arithmetic approach. The final 2 parts of this particular problem, parts D and E, look at the sum of a number of terms within the sequence. Part E, for example, asks students to find the sum of the first 144 digits or terms in the sequence. Now, this could be a very daunting task for a student at any level, including at ordinary level, and especially it could be daunting to a student that would be reliant on more rudimentary methods like systematic listing, for example. So here we see where simplification of the problem as a problem-solving strategy could be very useful. So rather than trying to answer part E directly, and calculate the sum of the first 144 digits in the sequence, a student might be guided or prompted or hinted towards maybe trying to work out what the sum of the first 12 digits or the sum of the first 18 digits in the sequence is. So if we take, for example, the simplified version of the problem, what would the sum of the first 18 digits be? A student might realize through a systematic listing approach that they're getting 27 plus 27 plus 27. So they're getting 27 3 times. So then they just have to work out how many times will they be getting 27 if they go all the way up to term number 144. So dividing 144 by 6 tells them that they'll get 27 24 times. And in that way, simplification of the problem allows them to reach a solution. And the teacher then could ask further probing or open-ended questions leading to higher level thinking, such as, well, how would you calculate the sum of the first x digits if x was not a multiple of 6? So instead of asking them to calculate the sum of the first 12 or 18 or 144 digits, what about the sum of the first 147 digits, which would be a slightly more complicated question again. The next problem 5 is a problem using the normal distribution. So as we read through the problem there for a few moments, we see that it appears a pretty standard question that will make use, given a particular context, of the normal distribution, of its symmetry, and of, at ordinary level, at Leaving Cert, the empirical rule. So a problem-solving approach that might be taken to help students deal with a question like this would be an approach that allows students to rely on their prior knowledge. And this is the approach known as generalization of the problem. So rather than the student just being encouraged to focus on the very specifics of the problem, which might be quite daunting to them, you know, the birth rates and things that they mightn't be, or birth weights rather, and things that they mightn't be very familiar with, encouraging students to look at generalization of the problem might make them feel that they're on more familiar ground. So in this particular example, the generalization would be that you have a random variable x. It's normally distributed with a given mean and a given standard deviation. So by the empirical rule, we know 68% of values lie within one standard deviation of the mean and 95% lie within 2 standard deviations of the mean. Students could be encouraged also to visualize what this looks like. So by sketching a bell-shaped curve and working with those percentages of a middle 68 and a middle 95%, they would be able to work out other percentages. In other words, 34% of values lie within 1 standard deviation of the mean and above the mean, and so on. And in this way, then, they would be able to translate their generalized representation of the problem to the specific example at hand. So, for example, to answer part A, rather than initially trying to work out what x minus y is, they would know that mu minus sigma is 2.92. In other words, the mean value minus 1 standard deviation brings you down to 2.92, because 2.92 was the lower value in that initial interval within which the middle 68% of the data lay. And then replacing mu with x and sigma with y, they have formed their first equation in x and y. And a similar approach allows them to form their second equation in terms of x and y, and then adding of the 2 equations or some other familiar algebraic method allows them to solve for x and y. And finally then, going back to the generalization approach, at Leaving Cert Ordinary Level, it's really the 68% and 95% rule. So there's a little hint really in the question that it might well be 95% that is the answer to part D. So would that work? Well, 95% would lie from mu minus 2 sigma up to mu plus 2 sigma. In other words, from x minus 2y up to x plus 2y. So substituting their values for x and y in, they would indeed end up with the correct interval. The next problem, and this will be the final problem I'll look at before our final problem, which we might have a look at together, is on the surface, as Mike has already pointed out, for us as teachers may be something that's very straightforward. In fact, a lot of us looking at this problem might, within a second or two, recognise that there's not really any calculation that has to be done. If you're familiar with the completed square form for quadratic function, you can actually answer the question immediately. But there are many different approaches before we even get to such direct methods that us as teachers might use that are perfectly valid and that students should be encouraged or could be encouraged to explore in a problem-solving setting. So let's have a look at some of the approaches that a student or students might look at to deal with this problem here. So one approach that could be taken to answer this problem would be to make out a table. And this mightn't even involve any manual calculation. It could just be making use of the functions functionality within modern calculators. So plugging in steps of 1, input values from 0 up to 8 or 9, using the function that represented the height of the golf ball, different heights get outputted. And a student then can see from that list that 46.8 is the largest of those. Now that is actually the correct answer, 46.8 meters, but a teacher at this stage, to try to generate some deeper or higher level thinking, could say to a student, well, will this particular method always guarantee finding the maximum height? And of course, the answer is no, because maybe the maximum height doesn't occur at one of the input values that you have used. Maybe it occurs sort of halfway or partially between one input value and another. Or a similar question, could you think of a question where this method wouldn't work? And that might get students then thinking about, okay, this method has worked here, but maybe I need to develop or explore other methods if the same type of question, but slightly different, came up in future. So a second approach that might be encouraged or students might engage in would be finding a pattern. So if using the function for height, students were to look, for example, at the first few heights separated by half-second intervals, they'd recognise that the pattern of heights that they're getting is not linear, because the first differences are not all the same, but the second differences are all the same and are not 0, so the pattern of heights is quadratic. That would allow a student or students then working together to continue this quadratic pattern to arrive at their maximum height, which you can see there is 46.8. And again, a teacher then might say, well, now, how do you know in this example, or rather using this approach, that 46.8 meters is actually the maximum height? What evidence is there in your quadratic pattern that is the maximum height? And that would encourage students to recognize that if they move a step either side of 46.8, they're landing at the same value, 45.55, 45.55, indicating that symmetry. In other words, that we have in fact reached the highest point. Another approach that could be taken might be an algebraic strategy. So students could be encouraged to make use of methods from algebra that they're familiar with, and their knowledge maybe of the symmetry of a quadratic curve or parabola. So an approach that a student might take would be to let the height function have a value of 0 in order to find the roots of the function. And by going through the usual process of setting up a quadratic equation with the square term first, the degree 1 term second, the constant term third, and so on, they could rely on a standard method like using the minus b or quadratic formula to come up with the 2 roots. Recognizing then that the maximum height must occur at the midpoint or halfway between these 2 roots due to the symmetry of the parabola, they'd be able to maybe sketch or visualize a graph of the height function, find out what that midpoint is, and use that midpoint as an input value into the height function. So that midpoint is in fact where x is 3, and plugging that in to the height function, they'll get their answer of 46.8 meters. And then this leads very nicely on to an even quicker or more efficient approach. And that could be motivated by the question from the teacher along the lines of, well, given your knowledge now of what this quadratic height function graph looks like, can you think of an even quicker approach that might make use of this knowledge that you could take to get the same answer? And that might lead students to a fourth approach, also algebraic in nature, but using calculus, where they'd be getting the first derivative of the height function, setting it equal to 0. Again, the teacher might be questioning them, well, why is this a useful step in order to optimize your function? And then going through the usual steps, they'll get the same answer, 46.8 meters. So there we see a number of different approaches, maybe becoming increasingly quicker, but all of them valid, that could be encouraged in problem-solving lessons with students. So finally, onto our final problem, which I'll put up on the slide on the screen now for us. It's a past Leaving Cert, a recent past Leaving Cert Ordinary Level question. I'll leave it up on the screen there for maybe a minute and a half to 2 minutes. And at the side of the screen on the right, you'll see the different problem-solving approaches or strategies that have been mentioned in the examples that we've seen earlier this evening. So what I'm suggesting we would consider for the next minute or minute and a half, maybe if you have a piece of paper and pen or pencil to hand, maybe just consider, are there 2 or 3 of those approaches that you think might lend themselves well to this particular problem, or that you think your students might be able to engage in this problem with? So I'll stop talking for a minute and a half or so, and then I'll come back to you and I'll take you through a few approaches that I think might be useful for this particular problem. So I think that's about a minute and a half there. So maybe you've picked 2 or 3 of those approaches from that list that you think might be suitable for your students or might be suitable for this problem. A few of the approaches I thought students might pursue were, firstly, the approach of trial and improvement. So recognizing that you're looking for a €960 annual increase in net income in order to get the required monthly increase, you could have an initial guess. So what if We's gross annual income was to increase by €2,000? In what situation would that leave her? Well, given that she'd only be able to keep 60% of this, her net annual income would go up by €1,200, which is too high. So then that leads us to reduce our next guess. So we might have a second attempt of €1,500 as the gross annual increase, but that would be a little bit too low, just giving us a net annual increase of €900. So we might increase the next guess slightly. And in this way, we'll arrive at the correct answer, which is €1,600. And students might be encouraged then to consider or to reflect on this method. So what would a drawback of this method be? So for example, in an exam situation, it mightn't be a method that will guarantee you getting the answer out in time. But likewise, what is an advantage of this method? And I suppose an advantage of this method is that it's something that a student might be able to fall back on in many situations if all else fails. Or it might be a way into a problem, and you could then use a different approach once you've cracked your way into the problem to actually get to a solution. Another approach I thought might be useful for this particular question might be drawing a picture where you use a rectangle to represent the original gross income, and then you add on the right an additional coloured rectangle to represent the increase in gross income. And given the fact that there is a higher rate of tax at 40%, that allows you to divide this coloured rectangle into 5 equal parts, 2 of which we can colour pink, and they'll be the ones that are going to the state in tax, and 3 of which in yellow we will be able to keep. And in this way, then the student visualizing the problem can recognize that, well, the 3 strips have to equal €960, so 1 strip must equal 320, and the 5 strips then that will give us the answer must be €1,600. And students then could be asked, well, okay, this is a great approach in this example, but can you think of a similar example where this method might not work or mightn't work so easily? So, for example, if the higher rate of tax was 41% rather than 40%, well, then you could still use this approach, but I think you'd have to divide your coloured rectangle into 100 equal strips and colour 41 of them pink and 59 of them yellow. So it's doable, but more complicated. A third approach might be an algebraic strategy. So probably, as Mike has mentioned earlier, the approach that most of us would jump to straight away, where X might represent the unknown increase in gross annual income. So 0.6 of X would have to be the required €960 increase in net annual income. And then a question that could be asked, I suppose, at this stage would be, was all the information stated in the original question even required to answer this particular question? So there was reference, for example, to €3,300 of tax credits. Was that something that was necessary for this particular question or not? So you might get students just to reflect on how they set up the problem and how they recognise what's important, what's not important. And a fourth approach that we haven't mentioned yet, but that could be useful here, would be the approach of solving the problem backwards, where you start with the end result and you work backwards to the beginning. In this case, the beginning would be the point where the gross annual income increases, and the end result would be the fact then that the net annual income has increased by €960. So working backwards, we know that 60% of the increase in gross annual income must be the €960. Dividing 960 by 60 will give us 1%, multiplying by 100 will give us 100%. So in this way, we can work backwards to what the original increase in gross annual income must have been. So in summary, hopefully from this presentation, Mike and myself have been able to look at some of the key issues around setting up problem solving, why problem solving is important, and in particular some of the different approaches, commonly used approaches that could be taken by students and under the supervision of their teachers in problem solving lessons. I won't go through each individual point that's here itself, but I suppose one of the things that has struck me just even in preparing this presentation is how I myself as a teacher overlook so many of the more rudimentary approaches that students might wish to take or might find it important to take for more difficult or unfamiliar problems, or just to crack into problems. I suppose as teachers, we're regardless of how much we try not to do it, we sort of inherently teach towards the exam, and we're always conscious of efficiency. But sometimes, you know, that's maybe putting the cart before the horse. And so I think exploring different strategies is very useful for students, to allow all students access problems, and also to help build resilience and confidence for students. They can see that there's not just one right way of doing something. So if the teacher is explaining something one way, well, maybe there are 2 or 3 or 4 other perfectly valid methods that could be used. Finally, before I hand you back to Connor, there are 2 very useful online resources that attendees this evening might be interested in having a look at if they haven't seen them before. One of them is the NRICH website that's managed by the University of Cambridge, that has loads of unusual and very interesting tasks and challenges, and has a whole section devoted to problem solving in which different approaches are discussed. And the second website is from the Mathematical Association of America, and it's the Curriculum Inspirations part of that website. Curriculum Inspirations is a section on this website that focuses in on different problem-solving strategies. There are loads of ready-made problems that are very detailed for teachers to use, accompanied by many useful online resources, including video presentations on the examples and on the approaches. So without any further ado, I'll hand you back to Connor.
Thanks so much, Jim, and thanks so much, Mike. I'm just going to share my screen. Get things in here. Hopefully you can see my Q&A slide there. So again, Jim, Mike, thanks so much for that. We have some questions, I think, coming in, and I do apologize. I'm going to have to move my cursor around. If anyone would like to post questions, you still have an opportunity to do that by either entering it through the chat button or Q&A. But to begin with, and I don't know who wants to take this first, but there's been a couple of questions that I'm noticing just coming about relating to the exam, the Leaving Cert examination itself. And here's an example of one that came in. It reads, is there really a need to practice problem-solving techniques with students given the short and predictable nature of Leaving Certificate Ordinary Level paper questions?
Can I take that one, Connor?
Absolutely, please, Mike.
Yeah, well, I suppose the first thing to say is that no matter what past paper you've been looking at, you will always find a few of those problem type questions. So in order to give everybody an opportunity and a chance to do well in the exam and to do those questions, then I think we should be practicing them in class. And I suppose further to that then as well, these kind of approaches, these different approaches to solving problems is going to help their general mathematics as well. You know, the so-called predictable questions that the person has asked about. Doing these questions, you're actually using those methods, those predictable methods to solve the problems, except obviously you don't know the answer straight off. So I would consider it very, very important, because not only does it develop their mathematical skills, it also teaches them or gives them the ability to problem solve and to think outside the box. And that's always going to be of benefit to the student. Even after they leave school, those kind of things that they learn through problem solving are going to be hugely advantageous to them.
Thanks, Mike. Another question that we have is, how can a teacher, quote unquote, teach problem solving techniques? Maybe Jim, you could take that one.
Hi, Connor. Yeah, hi everybody again. Yeah, I suppose it's really about just creating some space in the very busy timetable to explore different problem-solving approaches. It's really learning by doing, I think. As Mike has pointed out, the selection of useful and slightly unusual problems is very important, and making sure at the beginning of the process that students understand what it is they're being asked to answer. So giving students an opportunity at the beginning to ask those questions of clarification. And then the use of questioning during the process and while the teacher is supervising is particularly important, because you don't want to give the game away. You want students to have to persevere. You want them to build that resilience. So just making sure as a teacher that you're interjecting as needed, but not stepping over that line of just telling them, well, listen, this is all you have to do. I think also it's mentioned in the slides, but maybe something that we didn't focus on in the verbal presentations, making sure that there's plenty of time for students to reflect on their own work, whether that's on themselves in class or whether that's in small groups, and to also reflect on each other's work, so that they can see that there's a whole myriad of different approaches that can be taken. Some of them might be very basic, some of them might be very complex, some of them might be very time efficient, some of them might be very time consuming, but they all might eventually lead to the same result. I think that's very powerful for students, because I think a lot of students at ordinary level go into Leaving Cert with a feeling of, well, I'm only doing this subject sort of because I have to, and I'm not very good at it, I think, and you know, I don't get things straight away, and their confidence just generally in the subject isn't very high. So giving students a chance, I think, to reflect on each other's work and learn from each other's work and recognize that there is validity in various different approaches, I think that can be very very useful. So I don't think you teach it as such. I think you just try and create a space in which, over time, with practice, the skills are developed. You do have some input as a teacher, but I think it's really all about just creating that space and that time, and not trying to cram too much into it. If you're just doing an hour of problem solving, maybe once every 2 or 3 weeks, just to be doing a small number of problems, to be giving students the opportunity to really get into them and explore them and come away feeling more positive from them.
Thanks, Jim. We might just go for one more question before we wrap it up. So this is from a new teacher. I'm a new teacher in a new school and I'd like to try some problem solving in lessons, but I've no one to get support from within my school. Where do I start? I don't know whether Mike, maybe?
Yeah. I suppose the key thing, and we mentioned earlier on, is that you start small and you start with simple problems, especially at Leaving Cert Ordinary Level. If you want to get students to build their confidence, you've got to first of all give them some problems that is within their scope and within their ability to solve. I suppose as well, when we do give the problems, because of restricted class time and so on, we're inclined to jump in straight away and offer the solution. In other words, we're not giving them enough time to think about it. And I think, as Jim said there, it's all about giving them the space to solve the problem, not so much what we're teaching them, but allowing them to develop their own abilities themselves. I suppose as well, to encourage as much as possible group work and peer work. I just know from my own experience, and this comes from preparing maybe teams for team math and pie quizzes and all that kind of stuff. When you get the students together in small groups, practicing for those quizzes, it's amazing, you know, how they learn from each other. I know it's difficult when you have a class maybe of 30 to try to get them all into groups, but as Jim I think said there earlier on, it's not something you're going to do in every class every day of the week. It may only happen once a fortnight or whatever. And give them that opportunity to tease out the problems for themselves. So I think that's for a teacher that is starting off that with problem solving, that those are the kind of approaches that they should take.
Okay, thanks.
By the way, can I just say, just in preparation for this, I had a quick look at a few online sites, but a few of them have quoted Andrew Wiles, who solved Fermat's last term almost 30 years ago now. And if I could just read out what Andrew Wiles said about his experience of problem solving. So he says, perhaps I could best describe my experience of doing mathematics in terms of entering a dark mansion. You go into the first room and it's dark, completely dark. You stumble around, bumping into furniture. Gradually you learn where each piece of furniture is. And finally, after 6 months or so, you find a light switch and you turn it on. Suddenly it's all illuminated and you can see exactly where you were. Now, I don't think our students, 6 seconds is probably the max for those, but at the same time, it just gives you an idea of no matter what your ability is, even for professional mathematicians, they struggle with these kind of things every day of the week.
Yeah, I mean, I think that's really useful. It reminded me of my studies of maths, and like I'm a perfect example, maybe someone who would have struggled. I wasn't a fan of problem solving questions or anything that challenged me. And I think one of the things that's come through quite strongly from both of you guys today is you know, it's a skill that can be developed. And the area that I fell down certainly was, I think I lacked the perseverance. I'd go in, I'd try the question, and then if I couldn't, I didn't have, I suppose, the strategies perhaps to persevere. And so today, both Jim and Mike, you've talked about those strategies. You've talked about trial and improvement, looking for patterns, maybe applying the algebraic approach, and just giving yourself enough as the problem solver just to keep you going, as you describe in that metaphor of the house, Mike. And I suppose with more practice, you become more efficient. But critical to that, I guess, is also the teacher's role in that, and that they provide support, guidance, and those questions, you know, that you gave examples of, to just nudge the students as well along the way. So I thought that was quite appropriate, that example that you kind of reminded me of my own experiences of maths, particularly at Leaving Cert level. So I know it's run past, probably, I'm not sure exactly what time it is. It's running past 8:05. So I think we might wrap it up there. But once again, I'd like to thank Jim and Mike for what was a very informative presentation, covering, I think, what's a very important skill that needs to be developed in the study of maths, and really applies to you beyond that. Secondly, I'd like to thank everybody on the webinar. It's great to see such high attendance. It was fantastic. So to all the maths teachers with us today, thanks very much for joining us. I know it's an incredibly busy time. You're probably busy trying to wrap things up before the break, so we do appreciate you giving us an hour this evening. But I hope that you found it an hour to be well spent. Just another shameless plug of the book, but just to remind you that Active Maths 3, the new edition's out. So go to folens.ie if you have any interest in checking that out, or contacting your rep if you would like to learn a little bit more about the book and get a sample. For people who have asked, the video presentation is available. So if you've registered, even if there's people who haven't been able to attend, you will get a link to that video tomorrow to take a look at, and you'll get to look at the slides in a little bit more detail. And that's it, really. I'd like to just say thank you again, and from all of us here, this is myself, Mike and Jim, to everybody out there, thank you very much for attending, and we hope you enjoy the rest of your evening.